So welcome back. This is the lecture number 3, part 1 or A. And as I mentioned to you once, it's always very exciting to live in interesting times. And I remember I was kind of disappointed for many years that the life was so unexciting around the time I was living in communist Poland. Every day was the same, every year was the same, and nothing was changing. The life was gray and common and usual and very much predictable. Everything seemed to be, let's say, leading nowhere. You were standing in the one place and everything was, you were sure that everything will be the same tomorrow and after tomorrow. So now we have the nice situation. It is kind of a very exciting situation, and you should remember that. That's a crisis, a big crisis, and we predicted it. I remember we were talking about, and we predicted it, and now you have completely new situation. So we should understand that it's not going to be the same ever after the crisis is over. I believe that the things are going to change, and this is also a great opportunity to everyone. Those who know how to adapt, those who know how to, let's say, benefit these new opportunities, those will be the most successful. New stars, new experts, you will see what it will be. You will have a great career opportunities. Those who believe, let's say, that you will return to the normal like it used to be, it may be kind of disappointing. So I wish you all learn how to find out your own opportunity, how to figure it out, what kind of a future you can choose, and how this future will be basically taking advantage of what is happening now and benefit you. So with this optimistic accent, let me start my lecture. So as I promised, and I did this promise kind of a long time ago, that at certain time we will show that using the terminology analytic function to describe C-differentiable functions, it was completely legal, it was completely correct. And now we are going to do exactly this. We are going to prove that every C-differentiable function is indeed analytic, so we are allowed to call it analytic with no objections whatsoever. So let me begin and let me write it. Today's topic basically is concentrated around the following theorem. Let's write it down. Okay, sorry. Let me put it like this. Theorem, this was going to be our theorem. Not nice, I want to start nicely. Theorem. Underline, and this will be Taylor. Expansion. Theorem. So this is called the Taylor expansion theorem. Probably it is something that you already connect with the calculus, ideas from calculus when you were talking about the Taylor expansion. Let's do it. Okay, what it is. So let's start putting the things into the picture. Let U in C be a domain. This is a domain. And let's do it correctly. So we'll write it down. F, which is defined from U to C, be a C-differentiable function. I don't want to use analytic, as I remember. C-differentiable function. This is C-differentiable. Suppose we have a disk, suppose B, and I put here like this R, Z0 is an open disk, so this is the set of all Z such that Z minus Z0 smaller than R. We assume here that R is of course positive number, is such that this disk actually is contained in U. That's the disk contained in U. Okay? 10, I can write it down. The function f of z admits a power series expansion in this disk, which will be always convergent. It will converge in every point of this disk, admits a power series expansion. Let's say in this, okay, say f of z will be written like this. That's the power series expansion. N is equal to 0 to infinity, and this is an z minus z0 to the power n. And of course, this is, when I write equals, that means this infinite series for given z has a value. That means it's a convergent power series when this z belongs exactly to this br z0. And we can even describe what are these coefficients. Where, and let me write it down. An can be written as 1 divided by 2 pi I, and then you have here gamma. I will explain in a moment. This is f and this is w, and here we have here w minus z0 to the power n plus 1, and I put here dw at the top. And what is gamma? So where gamma is a positively oriented simple closed contour in BRZ0 containing Z0 inside the area bounded by gamma. So that is it. So of course all this theorem requires some picture. So this is the theorem. So what we are talking about? So first of all, I have here U. So I have a kind of a U. U is a domain. That's the domain of my function z. You see, I love drawings. You see drawings. So we take this whole matrix. This is not in the domain U. This is not in the domain U. Then that also. So we have a nice, let me put it like this, nice domain. Cartesian view. Now we have this point, this disk. So where I put this disk? Okay, I put here the z0 is here. The z0 is here. So now where is my disk? My disk, I can take the as big disk as possible. So I put it like that. This is my disk. This is my BRZ0. And now, where is my Z from this power series expansion? Z is here. Z is here. And now we take a contour. We can take any contour, but let's say we know that in the case of analytic functions, and we prove it, the integration doesn't depend on the contour. If two contours are homotopic, the integral will be the same. But just for our purpose, since I want to be, let's say, I want to be like more compatible with my proof that I'm going to do, I'll take the contour, which is a little smaller circle around the z0. So, and you see, this will be my contour gamma. This is my contour gamma. So I actually make the contour gamma like a little circle. So that means circle which has the radius, which will be, let's say, smaller than r, but still contains z and z0 inside. That's how it is. So this is my situation, and now that's your function f of z going here to. And this is our situation. So 10, we need to prove that there exists a power series expansion. So we will show that power series expansion of f of z exists in this BRZ0. So this is what we are going to do. So let's continue and let's write big letters proof. So now to do not lose the picture what we are doing. So I will just copy now. I copy this disk here separately. This is my disk. So we will keep it in mind what we are doing. So this is my point Z0. So this is my disk BR0. So assume that Z belongs to the BRZ0. So you understand, this is BRZ0. So I take the point Z. So I want to show that here we have here this particular formula. So power series expansion exists, which gives you exactly this value of f of z. Exactly this value of f of z. And that's what we are going to do. We'll find this power series. Okay, so 10. By Cauchy integral formula, I can write that f of z is equal, and I put here like this, 1 over 2 pi I. So this time I'm putting 2 pi I on the right. So you see that one will be kind of a contour gamma. So we know that the contour gamma has to contain z inside. So I put it like this. This is W. No bracket. So this is W minus z, and here I put here f w dz, and you see that's the Cauchy integral form. So gamma has to contain point z. Z is fixed. So here z. We make sure that we understand that we fixed it. Fixed. Z is fixed. This one. So we don't assume this is variable. So I'm using W to be my variable. I have this formula, so this is my formula. So I can also choose, so okay, let me put it like this. I have here z inside, so I can choose the gamma, because actually gamma can be anything, so I will choose the gamma as it was indicated above, as a smaller, slightly smaller circle. So this is my slightly smaller circle, so here will be the point W, and this is my gamma. This smaller circle contains both Z0 and Z inside, the area that gamma, bounded by gamma. So of course, that means I have this particular situation. So now I look at the function, and I consider this to be function of z of this particular expression. Maybe move it a little lower. 1 divided by omega minus z, which is exactly standing here. You see this is standing here, like 1 divided, so 1 divided by that one. So I remember we did couple in the previous lecture, we did couple of examples. Okay, we know how to make a power series expansion of this particular fraction with respect to the powers of z minus z0. We know it. So we will expand it. That means expand it. We expand too low. Expand into power series around z0. So let me do. So I know, I write it down like we did before. I put here like this 1, and here I have omega minus z0 plus, minus z minus z0. Yes, you see this can cancel that, so I'm getting exactly the same expression. So I can rewrite it down using the ideas that we discussed before. So I'm getting here 1, and this is times, and this is 1 minus z0 divided by omega minus z0. Oh, and we consider this particular expression as the 1 minus q, and here we write n is equal 0 to infinity q to the power n. So this is my q. This is my q. Okay, that one. And if this is my q, then I can use the power series expansion. This is now geometric series. And we are writing down this is equal 1 over omega minus z0. And here we have here n is equal 0 to infinity. And here we have here z minus z0 to the power n. And that one is omega minus z0 to the power n. And of course, we can simplify it, mainly put this omega here inside. So that provides us with the final expansion, and that we expanded this fraction. N plus 1. And now, of course, I have this expression equal to that expression, and I can plug it into this integral. So let's do it. So we are getting f of z is equal 1 over 2 pi I, and then I have this integral gamma, and then I have here the expression here. So, okay, so let's write it down. So I put here f of omega divided by, not divided, okay, so times, and here we have here n is equal 0 to infinity z minus z0 to the power n, omega minus z0 n plus 1, and I put here d omega. So now, one of the things that we learn, we can move this. Okay, let's move this one first inside this series. So let's do it just slowly. So we still understand what's happening. So put your f omega inside, and this will be z minus z0 to the power n, and this is omega minus z0 to the power n plus 1 omega. And now we learned it before, where because of the convergence of this integral. Oh, by the way, we didn't check the convergence of the series. So we have that this series converges. It's in the region of convergence. Does this series converges? Let me check. So what is my q? So q is supposed to be smaller than 1. So that means z minus z0 divided by omega minus z0 smaller than 1. And that means the z minus z0 should be shorter than omega minus z0. Maybe you cannot see it. That z minus z0 must be shorter than omega minus z0. So let's go to the picture. So where is z minus... Oh, this is this length. This is this length. And where is omega? Omega is here, so that is that one. So this one is shorter, longer. And that's exactly what is written here. So of course we have the convergence. Okay, so and therefore we are allowed to interchange. So it change sigma with the integration. And once we do it, okay, let's do it. So let me write it down. So this will be equal sigma, and this is n is equal 0 to infinity. This is equal 1 over 2 pi I. That's integral gamma, and this is f omega, and this is omega minus z0 n plus 1 d omega plus 1. And that one is equal to z minus z0 to the power n. So that means we just proved the theorem. That's it. This is your coefficient an, and as it is listed here, see, this is exactly this formula. This is exactly this formula. This is exactly this formula. Yeah. So we got the power series expansion. Please notice. Notice. So put it like this. Remark. By comparing the coefficient, the formula for an by the Cauchy, generalized by the generalized Cauchy in formula, generalized Cauchy integral formula, means that an actually is equal to f n derivative at z0 divided by n factorial. Indeed, just remember that this integral that appears there, this is f of omega, and this is omega minus z0 to the power n plus 1 d omega, what it was? It was 2 pi I divided by n factorial, and this was equal to f of, f n derivative at z0. So that's exactly this formula. So that exactly coincides. So this formula coincides with Taylor formula that we have studied in calculus. So that's how it is. So that's how it is. That's how it is. That's no difference. This integral was just used to show that we actually are getting here power series expansion. So maybe let me make the corollary. This is important corollary because now we can conclude corollary. And let us conclude it. Every complex C-differentiable function is complex analytic. Every complex C-differentiable function is complex. Yeah, that's a great thing. Just remember, remark. Just, you should remember that there are real differentiable functions. Even infinitely differentiable functions. Which are not analytic. One of those examples that I assume you have seen, so put it like this, for example, f of t is equal, let me write it down, 0 if t is smaller equal than 0, and this will be e to the minus 1 over t if t is larger than 0. I take this function. So it can be verified. Look, you can even show you the graph of that function, how this function looks like. So this is the coordinate system. This is, for example, 1 is here, so we have here asymptote. Yeah, and how it goes. So we have here the graph. So here is 0, 0, 0, and here it starts going up and changes in asymptote. Oh, this is the function. It's smooth, means derivatives exist, not analytic. Not analytic. It's not analytic at this particular point here. Power series gives you all derivatives equal to 0, but function, you see, on that side, on the right side, it's not 0, so it cannot be equal to the power series expansion. Again, you will get that power series expansion at this point is composed of all 0, 0, 0, 0, 0 power, 0 first power, 0 second power, 0 third power, and that means function is not 0 here, so how it can be equal to 0 equal to something what is not 0. So it's not analytic. So that's kind of a good thing. So you can say like this, that conclusion, complex C-differentiable functions are perfect. Are differentiable functions are not So that's why we love complex functions. Oh, so that's a nice conclusion. This is a very nice conclusion to conclude why the functions, complex differentiable, complex analytic functions are so beautiful. Why they're so nice. They're so geometric. They're so perfect. So that's kind of a, for you, when you are first time finding something perfect, you just don't believe it's possible. Yes, it is possible. We have the perfection here. So let's continue. So once we figure it out, so now we can say the conclusion. First conclusion and conclusion. All elementary, basic, elementary, complex functions are analytic. And we can write it down. So, and we can find their power series, and they admit power series expansions, of the type. So we know exactly how to expand those functions. So we write it now. So this will be coefficient will be at z0, this n derivative n factorial, and here we'll write it down z minus z0 to the power n, n is equal to 0 to infinity. That's how we do it. So what are those basic elementary functions? Okay, let's start. Start with the function f of z is equal sine of z. Okay, so how to do it? So there are two ways we can do it. But I can use that one because this is kind of an easy one by using the derivative, because you can find easily that the derivative of the function cosine, and I put here n derivative of the function cosine, of the function phi sine of z, what it is. So you can verify it. This is a kind of the same formula as in the calculus. This will be z and that plus n, put it like this, n times pi over 2. So this is n times pi over 2. Yeah, it's because I want to write, actually, if I'm interested in the point z0, this will give me the derivative of the point z0, so I can write a general expansion of the function sine at any point. So thus I can write it down, sine of z is equal, and then I can write it down, this is the sum, n is equal to 0 to infinity, and then I have here sine of z0 plus n pi over 2 divided by n factorial z minus z0 to the power n, and that's a power series of expansion. Yeah, I know it looks a little different from the one that we learn in calculus, because in the calculus we're just simply considering consider the sinus as a power series with respect to powers of z. So that's also very easy to find. So maybe you should remember it also can be written for z, this one, sorry, for z0 is equal to 0, so this will be n is equal to 0 to infinity. Here we'll have minus 1 to the power n, and then you have here z to the power 2n plus 1, and here we have here 2n plus 1 factorial. So yeah, that you can do it like that. Of course, there are other ways of doing it, so I will show you in a moment how to find the power series expansions also. But let me do the same things for cosine of z. Cosine of z, and then you notice that cosine dZn dnz of not I have to raise it. Oh, it's not good. Maybe I should. Oh, I'm raising. Since dn, and this is dzn of cosine z0 is equal to cosine, the same formula. So I have the same formula here, except replace cosine, sine by cosine, and you are getting cosine z0 plus n pi over 2. And now, of course, remember, of course, you can just say that I derived this formula using, one second. I derived this formula from that formula by plugging z0 in the previous one. Of course, it works that way. Let me make sure. And this will be n factorial, and this will be z minus z0 to the power n, and of course cosine of z is equal to, and we have here n is equal to 0 to infinity, and I put it like this, minus 1 to the power n, z to the power n, and this will be 2 to n factorial. So that's another formula for z0 is equal to 0. Similarly, let's take the function ez, and here ez dzn n of ez is equal to ez, so therefore we are getting here that this one is equal, n is equal to 0 to infinity, and that one is equal e to the z0 divided by n factorial, and this will be z minus z0 to the power n. Or you can do it differently. So of course you can also write it down like that. This is e z is equal to, by similar, at z0 is equal to 0, so this will be z to the power n divided by n factorial. And of course, if you use, for example, the idea that this one is equal to z minus z0 plus z0, so this one is equal ez0 e z minus z0, then you use this formula for that one. That means substitute that guy by that guy, so you will get that this gives you again the formula. This is ez, and 10, this is n equals 0. So this is sigma n is equal to 0 to infinity, and I put here z minus z0 to the power n factorial, and you see, wow, this is actually the same that is here. So I got the same here. So that means, yeah, it is possible. Another way, so let's use this expansions and let's play a little longer. So let's find another expansion. For example, let's go back to sine. Let's say sine of z, and try to do it again at the point, any point z0, at any point z0. So I say, what do I have here? I say, I have here the following. So I want to do it at the point z0 in the differential. So first of all, I remember what is sine. This is iz minus iz divided by, by 2I. So I can take this 1 over 2I out, and let me use the same idea as I did before. So I'm getting here, this will be like a e, and I put here I, and this will be z minus z0 plus z0, and this is minus e minus I, and this will be z minus z0 plus z0. This is still the same, yeah. So I'm getting the first one is so 2I, and that one, what we did is just before, so I can put it like this is E, and I'm getting here I z0, and then I have here sum n is equal 0 to infinity, and I have here I z0, so that means it will be like a I to the power n, I to the power n, and this one will be equal z minus z0 to the power n. So this is exactly what is written here, z to the power n, and this is all divided by n factorial. And then you have minus, and this is minus ei z0, and similarly n is equal to 0 to infinity. And this is minus I to the power. So this is minus I to the power n, this is z minus z0 to the power n, divided by n factorial. Of course, we can arrange everything nicely. 1 sigma for all, and then we are getting here 2I. This will be that guy from here. This 2I goes now here, and then I have this and this, so put them together, and I'm getting I to the power n, ei z0, and this is minus e minus I z0, and this one is, I forgot. Where's my I? Erase. It's not erasing. Good. One. Doesn't want to erase. Sorry. Minus I to the power n, and this is ei z0. You see, it does not want to erase this. Computers, minus. This is minus. Those computers, I have no comments. Z minus z0 to the power n. They are supposed to work. And can you see, what did I get before? What did I get before? I got this formula. I got this formula. Certainly, you should understand. I just computed that expression. So something else is missing, of course. N factorial. So we did computations of other expressions somehow differently. And I tell you, notice that this one, notice. You can simplify it. Notice that this sign, and this is z0 plus n pi over 2 is equal, so well, I have that guy, so this is equal over 2I. This is in I z0 minus I to the power n. 1, 2, 3, 4, 5, 6, 7, 8, 9, downwards. E I z0 minus I to the power n, E minus I z0. So just notice that this is a real number. And it can be simplified. You can simplify. Can be simplified. I'm not doing it. You can do it. It has to be done, kind of. And you will get exactly the same the same value as it is there, except in different, you will get it in different trigonometric form. This is, I tell you something, it is not at all providing you with kind of a simplification, real simplification. No, that's the same formula. There's a different trigonometric formula. It doesn't allow you to compute this value. Okay, so we did it. So maybe let me check a few other things. Let me see if I have another examples here. Yeah, I think so. Yeah, cosine hyperbolic, sine hyperbolic. So let's go to the next one. Just simply, this is the same as in the case of the ordinary function, n is equal to 0 to infinity. And then, what do I have here? What is cosine? It was even power. And then 2n factorial. So the only difference, there is no minus 1. So sine hyperbolic of z will be also the same as in the case of the real functions. So it will be just z to the power 2n plus 1 divided by 2n plus 1 factorial. Maybe another remark. You remember we did this one, 1 minus z. Do you remember it? 1 minus z. What is 1 minus z? 1 minus z. This was equal to just simply z to the power n is equal to 0 to infinity. What about the 1 plus or 1 over z? This is equal to n is equal to 0 to infinity. And that one is equal to z. Minus 1 to, it's not working. See, you cannot erase it. So 1 plus z is equal to n is equal to 0 to infinity minus 1 to n z to the power n. So now let me ask you a question. What is antiderivative of 1 divided by 1 minus z? Antiderivative. So we have it. Any branch of logarithm, I put here minus 1 minus z is equal to 1 divided by 1 minus z. And logarithm of 1 plus z is exactly equal to 1 plus z. So in a certain way, by integrating, by taking antiderivative term by term, you obtain that the logarithm, start with that one, of that guy, so 1 plus z is equal. So of course, remember, every integration has a constant term, constant. So in our case, this will be the constant term. You have to write this as logarithm of 1. You take z, 0 is equal to 0, so you plug it in, and plus, and then you are getting also n is equal to 0 to infinity, and minus 1 to the power n, and integrate, take antiderivatives term by term. So that means simply you are getting z n plus 1 divided by n plus 1. N plus 1. And similarly, you are getting log of 1 minus z is equal, and this will be again log at 1 plus, and this will be n is equal to 0 to infinity. I think we should change it to minus, because here will be this minus here, and this will be z to the power n plus 1 divided by n plus 1. So, in other words, we have the formula. So for example, if you know that f of z is equal to n is equal to 0 to infinity a n, and this will be z minus z0 to the power n, and suppose that f prime of z is equal f of z, then you can find the power series expansion of f of z, just simply saying that this is f of z0, that must be here, and then this is n is equal 0 to infinity, and this is a n divided by n plus 1, and this is z minus z0 to the power n plus 1. No? That's what we were using. That's what we were using here. So finally, let me make a couple of observations. So one of the observations is this one. Call it remark. Notice that for any elementary function that we just consider, we have, and that's not only here, because those are the functions that actually we can compare. We have that, first of all, you take z and you can write it down. You have here power series expansion. You can write it down a n, and then you have here z. Try to erase it. 1, 2. Z to the power n, and you can write it down in the terms of n is equal 0 to infinity, and this is a n x plus I y to the power n. So if I take here, instead of n, I put here x0, consider this as a function of two variables, x and y, so I will be getting exactly the same power series expansion, except I replace z by xn. So what is the purpose of comparing these two power series? They are exactly the same. So the power series are the same. We just need to replace one symbol by another. So what is one symbol? Like x by another z. So you're just getting the same thing. So that means simply, if you know, therefore, that the function f depending x and y is analytic, the formula given by f of x0 can be converted to formula with respect to variable z. Put it like this, f of z to variable z by replacing x by y by z. And that was exactly what we were doing. By replacing that one by this one. This is what we were doing. And now, as you see, you don't need to verify anymore. Once you know that function is analytic, you can just simply do it. Yeah. So maybe that's a good moment to finish this part of the lecture, and in the next lecture we will concentrate on the further properties of the analytic functions. We will talk about some of the, let's say, important terminology like zeros of analytic functions, the multiplicity of the zeros, and the properties of that the two functions that coincides on a set containing an accumulation point. They are coinciding everywhere in the connected domain. They will coincide everywhere in the connected domain. So, thank you, and see you again.